In our second circuit, we have combined a NOT, two AND gates, and an OR gate. We have two inputs, A and B, and an output labelled F. We need to walk through each combination of inputs A and B to determine the truth table for this circuit. We will begin with A and B set at 0. A sends a 0 signal to the NOT gate. The NOT gate inverts the signal to a 1. So the first AND gate receives a 1 signal from the first input. B sends a 0 signal to the first AND gate. Notice that a wire branches from A to the second AND gate. A will send a 0 signal to it. B also has a wire which branches off to the second AND gate. B is also sending a 0 signal. The first AND gate will be receiving a 1-0 signal, so it will output a 0. The second AND gate will receive a 0-0 signal, so it will also output a 0. This means the OR gate will receive a 0 signal from both AND gates and will produce a 0 output at F. We now have the first entry for the truth table. A 0 signal on A and a 0 signal on B will produce a 0 signal at F. Let's now set the input on A to 1 and the input on B to 0. The 1 signal from A is inverted by the NOT gate and becomes a 0. So the first AND gate will receive a 0 signal from A and from B. The second AND gate will receive a 1 signal from A and a 0 signal from B. So both AND gates will output a 0 signal to the OR gate. With the OR gate receiving 0 signals on both inputs, a 0 signal will be produced at F. We can now add this to the truth table. A 1 signal on A and a 0 signal on B will produce a 0 signal at F. Let's now set the input on A to 0 and the input on B to 1. The 0 signal from A is inverted by the NOT gate and becomes a 1. So the first AND gate will receive a 1 signal from A and from B. The second AND gate will receive a 0 signal from A and a 1 from B. So the first AND gate will receive a 1-1 signal, and the second AND gate will receive a 0-1 signal. The first AND gate will send a 1 signal and the second a 0 signal to the OR gate. A 1-0 signal will turn the OR gate on and will now output a 1 at F. Let's update the truth table. A 0 signal on A and a 1 signal on B will produce a 1 signal at F. Let's now set the input on A to 1 and the input on B to 1. The 1 signal from A is inverted by the NOT gate and becomes a 0. So the first AND gate will receive a 0 signal from A and a 1 from B. The second AND gate will receive a 1 signal from A and a 1 signal from B. So the first AND gate will receive a 0-1 and the second AND gate will receive a 1 1. The first AND gate will produce a 0, and the second AND gate will produce a 1. A 0, 1 signal will turn on the OR gate and it will allow it to output a 1 at F. We can now update the truth table. A 1 signal on A and a 1 signal on B will produce a 1 signal at F. Let's go to the simulator to see the working model. Here is the circuit we viewed in the slides previous. It has two inputs, A and B, and at the output there is an LED with a current limiting resistor. Let's test the circuit to see it matches our truth table. Inputs A and B are set to 0. When the simulation is started, the LED does not light up, so a 0 signal is being produced. Let's now change input A to 1. No output. Let's change A to 0 and B to 1. The LED lights up. And finally, let's set both A and B to 1. The LED lights up. This matches the truth table we created earlier. So as we have seen, we can combine logic gates to make a different type of truth table to control circuitry. Now that we understand single logic gates and how we can combine them together, we can move on to more complex circuits. In the next video, we will look at how we can use logic gates to create a binary adder. I hope you have enjoyed this video. Please feel free to ask questions and leave comments. All the best.